Okay, so this is a second video about alternating series. We had the alternating series test explained in our past video, and you can check it out. If not, I'll just copy paste it here, or show it right here. This is the alternating series. It said that if you all you need is series to be alternating to check that it converges. All you need to do is to check that the bn's are decreasing. It's a decreasing sequence, and the limit is 0. Remember that under this umbrella, let me go over here. Go over here. Oops, something happened to my turn series. Let me put this right there. Remember that under this umbrella, we are thinking that my bn's are positive. Okay. If not, this doesn't make any sense. Okay, so something when we did the proof of this that this test works, we saw that B1 actually was an upper bound for the partials for the partial sums. For this. And so we'll explore that idea more a little bit. So remember that this means I have an alternate series of the form of B1 minus B2 plus B3 minus B4 and so on. I'm going to write a few, and that's it. Remember also, sorry, this should be B7, looks like a BZ. Remember also that we're saying always that it's decreasing, so the Bn plus 1 is less than the Bn. So as you go down this list, they're getting smaller in absolute value, right? Because it's negatives, some of them. Okay, so let's explore this idea a little bit, like I said. So I have the number line right here, pretend this is just a number line, and I'm going to have a sum. So when you add the first term, you get S1. It's a number right here, right? That's S1. Now when you add two terms to get S2, you subtract in V2, so it's less than S1, right? So once you add it, you're going to go and get somewhere over here, and that's S2 when you add two terms. Now when you add the next term to get S3, you're going to add B3, but remember that B3 is smaller than B2. And this distance here is B2, right? Because I moved B2 to the left. So I'm going to add B3 now, but B3 is smaller than B2, which means that when I'm going to add something, I'm not going to hit S1. I know I'm going to be to the left of S1, right? Because this distance between this 2 and S3, this is B3. And B3 is smaller than B2. With the same reasoning, I'm now going to subtract, if I add the first four terms, no, let me overlapping here, but if I add the first four terms, right, to get what is S4, the new term is subtract B4 from what I had, and B4 is smaller than B3. So if this distance was B3, I'm going to subtract something that's smaller than that, so I'm not going to make it further to the left than this 2, right? So this is going to be S4. So continuing with this idea, you can see that I'm going to know that my real sum is somewhere between these numbers, right? If I stop only the first four terms, the value of if I have a series that is convergent that follows the two conditions, that is decreasing and then limit is 0, then the limit exists, and that limit has to be somewhere in here. And if I add the next term, I'm going to be adding B5, which is smaller than B4. So I'm going to add somewhere here, right? So all we're saying with this idea is, and it's very powerful, is that the remainder, remember that the remainder is, if adding the first n terms, is just a difference between the actual sum and the partial sum of 2n. Sorry, if I use that n, I should use the same n. So we're saying that it's always going to be smaller than the next term. So we have a very easy way to bound the remainder in this case. Very easy. It's just smaller than the next term. Because if I stop in the fifth, the real sum is going to be somewhere between that and the next term, right? And if I stop in the sixth, the real sum is going to be somewhere between that one and the next one, following this idea. So it's a very, very simple idea. So this is our remainder estimate for alternating series. Very, very powerful and very simple. So we probably noticed this. We didn't talk about this, but in my previous video. But you probably noticed that something strange is happening in terms of the harmonic series. We know that this one does not converge, right? Harmonic series. But now, if we make it alternating, we add a term that's changing the powers. Let's put it like that. This one does converge. Right? This one does converge. Why? Well, simple, because the Bn is 1 over n, and is check that is decreasing easily, right? This is, and the limit is 0. Those are the only two things we need to check for alternating series to converge. So it's given. It's very easy. But now we know something even more, that, for example, if we want to estimate using the first 10 terms, say, what I'm saying is S10 would be n equals 1 to infinity of negative 1 to the n plus 1 over n. Sorry, I said S10 and I put infinity. I'm stopping at 10. Well, you know what that means. This is going to be a 1 minus a half plus a third minus fourths and so on until the positive ninth and the negative 10th. So if you don't want to know what that sum is, I'm going to do it in my computer over here. Sorry for not having this ready. But I'm going to add this. I'm going to do the sum from n equals 1 to 10 of negative 1 to the power of n plus 1 divided by n. So I get 0.645. Let me do 64563. Okay. But what we just talked about, now we know that the remainder is smaller than, very easy, the next term, which is 1/11. And as a decimal, 1/11 is 0.90909. So now you have a good estimate of the sum. You know that this is approximately the sum, and we knew a lot. We know that if you follow this idea of my term was your S1 is here, S2 is a negative, S3, so all the odds S partial sums up to number of terms are overestimates, and all the evens are underestimates. So you know this is an underestimate, right? Because we're going to be in this practice, you're going to go S4, S1, S2, S3, S4, S5, S6. So S10 is going to be on this side, and the real sum is going to be to the right. So you know that the real sum is somewhere between this number and that number plus this. So if you add a 09, let me put it right here, 6, 4, 5, 6, 3 plus 0.09, 09, 09, right? So it's not just this, you know that you're having this 10 as an underestimate, and you add this. So the real sum is somewhere here. Okay? So that's something to use with estimates of the remainders in this case.